On March 6, 2026, a groundbreaking paper was submitted to Nature, one of the most prestigious scientific journals on Earth. But this wasn't just any paper. It wasn't a preprint or a conference presentation, it was a revelation. This research came from NASA's Goddard Space Flight Center, and it involved data from none other than the James Webb Space Telescope. The findings were nothing short of astonishing. The water within a small celestial body, known as 3I Atlas, contained 10 times more deuterium than any comet ever measured in our solar system. 10 times. Now, you might be wondering, is that number a mistake? An error in measurement? No. This finding is 12 standard deviations above the mean of all known proto-stars in the Milky Way. It's significant and unambiguous. The only object in our solar system with a similar deuterium ratio is Venus, but Venus reached that through billions of years of atmospheric escape. In contrast, 3I Atlas, a 2.6-kilometer ball of ice and rock, has no atmosphere and has been drifting through interstellar space for longer than Earth has existed. This begs the question, where did all that deuterium come from? According to the paper, 3I Atlas formed at temperatures below 30 degrees Kelvin, a mere 30 degrees above absolute zero. It originated in a stellar system that was poor in heavy elements during the early stages of the Milky Way's history, between 10 and 12 billion years ago. This is where it gets truly mind-boggling. Our Sun is 4.6 billion years old, and Earth came into existence just a little later, around 4.5 billion years ago. In comparison, 3I Atlas was already ancient before our solar system even started forming. Here's the fascinating part. When 3I Atlas passed through our solar system, scientists took a close look at it, and what they found was unlike anything ever measured in any other object in the solar system. Now, let's dive into what deuterium is and why its abundance in 3I Atlas is so significant. Hydrogen, the simplest element in the universe, consists of just one proton and one electron. It makes up about 75% of all ordinary matter in the universe. Stars fuse hydrogen to create helium, and water is made from hydrogen and oxygen. Deuterium, often referred to as heavy hydrogen, is a variant of hydrogen. It has the same proton and electron as regular hydrogen, but it also contains a neutron in its nucleus. This makes deuterium twice as heavy as regular hydrogen. Now, let me take you through why the deuterium to hydrogen ratio matters. After the Big Bang, the universe was born with a fixed ratio of deuterium to normal hydrogen. For every 40,000 hydrogen atoms, one of them is deuterium. This primordial ratio was set in the first minutes after the universe's formation. But what does that mean in simple terms? Stars gradually destroy deuterium by fusing it alongside regular hydrogen. Over time, this depletes the deuterium content in the galaxy. In our solar system, the deuterium-hydrogen ratio in comets ranges from 0.03% to 0.06%. That's a bit higher than the water we find on Earth, which has a ratio of about 0.016%. This is well understood astrochemistry. Colder environments tend to incorporate more deuterium into water ice. The colder the environment, the more deuterium gets locked into the water. This isn't just speculation. This is backed by extensive research in the field of astrochemistry. Now, here's where 3I Atlas shatters all our expectations. The deuterium to hydrogen ratio in the water of 3I Atlas, as measured by the James Webb Space Telescope, is 0.95%. That's almost 1%. To put this into perspective, that's not just a slight increase, it's an order of magnitude higher than anything we've seen before in any solar system body. It's 12 standard deviations above the mean of all measured protostars. The paper describes this composition as unlike any solar system body. That means, plain and simple, we've never seen anything like this. So, what does this extremely high deuterium ratio tell us about the formation of 3I Atlas? Let's break it down. The relationship between the deuterium-hydrogen ratio and the temperature at which the water formed is clear. A higher deuterium ratio indicates a colder formation temperature. For comparison, water ice in solar system comets with a deuterium ratio of 0.05% formed at temperatures between 20 to 30 Kelvin, already extremely cold. But for 3I, Atlas with its deuterium ratio of 0.95%, the model suggests that the temperature during its formation was well below 30 Kelvin, likely much colder. This temperature range suggests that the water ice in 3I Atlas didn't form in a protolunar disk like other comets in our solar system. Instead, it formed, or at least underwent its final isotopic exchange in a pre-stellar dense core, an environment far colder and denser than the outer reaches of a planetary disk. This pre-stellar phase of star formation occurred before any stars had even ignited in the vicinity. It's one of the coldest phases in the formation of stars, with temperatures hovering between 10 to 20 Kelvin. In these conditions, cosmic rays are partially shielded, and it takes hundreds of thousands to millions of years for the molecular cloud to collapse and form a stellar system. What's truly extraordinary here is that the water ice in 3I Atlas preserves a chemical memory of those conditions. It was processed in a pre-stellar core, then incorporated into a planetesimal during disk formation. It retained its isotopic signature because it was never subjected to the thermal processing that would have caused deuterium re-equilibration. For billions of years, this planetesimal has been drifting through interstellar space, carrying with it a record of the early days of our galaxy. And then, as 3I Atlas passed close enough to the Sun, it released these molecules into space, and we were able to measure them. This is a profound moment in astronomy. The molecules in 3I Atlas aren't just foreign because they came from another star system, they're from another era of the Milky Way. These molecules carry a message from 10 to 12 billion years ago, when the galaxy was a much younger, colder, and metal-poor place. This is the earliest snapshot of the Milky Way we've ever gotten, preserved in the water ice of 3I Atlas. The implications of this measurement go beyond just understanding the chemical composition of a single object. It's about understanding the history of the universe itself. For the first time, we have direct physical evidence of the conditions that existed in the early stages of the galaxy's formation. The fact that we can study these ancient molecules opens a new chapter in our understanding of the origins of our own solar system and of the galaxy itself. This is a moment in time that has never been observed before. As we continue to explore the extraordinary details of 3I Atlas, we now turn our attention to another key measurement, the carbon isotopic ratio. Carbon, the building block of life as we know it, comes in two stable isotopes, carbon 1,2,12C and carbon 1,3,13C. The ratio of these isotopes is a crucial tool for understanding the chemical evolution of galaxies. Over time, stars produce 13C during their life cycles and release it into the interstellar medium when they die. This process enriches the galaxy with heavier elements like 13C, and the ratio of 12C to 13C gives us a clock for galactic evolution. In our solar system, the 12C-13C ratio is about 89. In solar system comets, it typically ranges between 90 and 120. But when scientists measured the 12C-13C ratio in the gas released from 3I Atlas, The results were astonishing. The ratio ranged from 140, 1 to 191, for CO2 and from 123 to 172 for CO. These numbers are far higher than anything we've observed in the solar system or nearby interstellar molecular clouds, where the ratio typically ranges from 60 to 80. So, what does this mean? A higher 12C, 13C ratio indicates that less stellar processing has occurred. In simpler terms, it means that fewer generations of stars have lived and died in 3I Atlas's region of the galaxy, enriching the interstellar medium with heavier elements like 13C. This suggests that 3I Atlas formed in a much older, less evolved region of the Milky Way, likely in the first few billion years of the galaxy's existence. The carbon isotopes in 3I Atlas confirm that this object is not just ancient, but it came from a time before the Milky Way had undergone the cycles of stellar birth and death that enriched the galaxy with heavier elements. This discovery adds another layer to the mystery of 3I Atlas. It's not just a comet from another stellar system, it's a time capsule from the early universe carrying with it the signature of a time when the galaxy was still young, with fewer heavy elements. The carbon isotopes further reinforce the idea that 3I Atlas didn't form in the same conditions as objects in our solar system. It formed in a galaxy that was much poorer in metals and heavier elements than the one we live in today. Now, you might be wondering, how do we know that 3I Atlas formed in such an ancient, low metallicity environment? It's all about the isotopic data. The measurements from the James Webb Space Telescope, combined with other data from different instruments, point to a consistent picture. The paper submitted to Nature points out that the isotopic composition of 3I Atlas matches the conditions of an early Milky Way, one that existed 10 to 12 billion years ago, a time before the galaxy had gone through the cycles of star formation and supernovae that enriched the interstellar medium with metals. The implications of these findings are profound. For one, it tells us that the early Milky Way was a much harsher and colder place than the galaxy we know today. It also means that 3I Atlas is a rare remnant of this early galactic history. The object has preserved the chemistry of the universe's youth, carrying with it information that we couldn't have otherwise obtained. This is a snapshot of the galaxy at a time when conditions were vastly different from what we see around us now. The discovery of 3I Atlas's isotopic signature has the potential to reshape our understanding of the early Milky Way and how our solar system came into being. As we move forward, one crucial question remains: what else could we learn from objects like 3I Atlas? Could other interstellar objects carry similar messages from the past? And what does this mean for the future of astronomy? The discovery of 3I Atlas's unusual isotopic composition doesn't just end with carbon and deuterium measurements. It opens the door to even more exciting possibilities. One of the major questions raised by this discovery is whether other interstellar objects, like 3I Atlas, could provide similar insights into the early days of the Milky Way. If 3I Atlas is truly a remnant of a different era in the galaxy's history, it stands to reason that other objects traveling through our solar system could also carry traces of the past. This is an important realization because, until now, astronomers haven't had many opportunities to study objects from outside our solar system with such high precision. 3I Atlas is the first interstellar object to be studied in such detail, thanks to its high activity and the advanced capabilities of the James Webb Space Telescope. But what if we could measure the isotopic compositions of other interstellar comets or asteroids before they pass too far from Earth? The next time an interstellar object passes through our solar system, scientists will know to prioritize isotopic measurements especially before it reaches perihelion, the closest point to the Sun, where the surface volatiles may be depleted. One of the most intriguing aspects of 3I Atlas is its potential to change the way we look at organic chemistry in space. The paper notes the presence of methanol, hydrogen cyanide, HCN, and other organic molecules in the object's outgassing. These molecules, which are building blocks of life, were detected in the gas released by 3I Atlas as it passed through our solar system. Could the organic molecules in 3I Atlas also carry unusual isotopic signatures, just like the water and carbon? If so, this could have profound implications for our understanding of prebiotic chemistry in space. A key aspect of prebiotic chemistry is the role that heavy isotopes like deuterium and carbon-13 play in the formation of amino acids and other organic compounds. Isotopic enrichment in organic molecules affects their behavior in polymerization reactions. For example, deuterium-enriched amino acid precursors behave differently in reactions than regular ones. This could mean that the organic molecules in 3I Atlas might have unique chemical properties that could offer clues about the origins of life elsewhere in the universe. This opens up a whole new area of exploration. If future interstellar objects contain organic molecules with similar isotopic enrichments, it could mean that they're carrying the raw materials for life in a form we've never seen before. This is an exciting prospect for astrobiology, as it could offer us the first direct evidence of organic chemistry from beyond our solar system. The potential for discoveries in this field is immense, and 3I Atlas is just the beginning. Now, as we look ahead, we must ask, what else might 3I Atlas reveal in the coming months? With the upcoming Jupiter flyby just around the corner, scientists are preparing for the next set of measurements. Could 3I Atlas release more clues about the early history of the Milky Way? Could it help us answer the most profound questions in astronomy? We'll have to wait and see. The excitement surrounding 3I Atlas doesn't stop with its current measurements. In fact, as this small but mighty object makes its way past Jupiter and towards Saturn, then Uranus, and finally into the vast reaches of interstellar space, the window to study it is rapidly closing. With each passing day, the opportunity to observe and measure 3I Atlas becomes more limited. Its trajectory, moving deeper into space, will soon take it out of range of the instruments we've used to study it, especially the James Webb Space Telescope. In just a few short days, 3I Atlas will fly past Jupiter, a critical moment for astronomers who are closely monitoring the object. This flyby could provide one last chance to gather important data before the object accelerates further into the cosmos, never to return to our solar system. The flyby will provide invaluable insights into the object's composition, as its interactions with the gravitational field of Jupiter might alter its trajectory and reveal even more about its origins. This moment, once it passes, will be irreversible. Afterward, 3I Atlas will continue its journey across the galaxy, leaving us with only the already collected data that could change our understanding of cosmic history forever. This also raises the question, what happens after the flyby? After 3I Atlas moves beyond Jupiter and into the outer solar system, it will continue its journey into the vast expanse of interstellar space. For all intents and purposes, 3I Atlas will leave our cosmic neighborhood and become a distant relic, drifting silently through the stars. We will never have the chance to measure it again, and its secrets will remain locked away. But in the time we've had with 3I Atlas, we've learned more than we could have imagined. The information we've gathered from this passing object has already expanded the frontiers of our knowledge about the early days of the Milky Way. It's preserved the chemical memory of a time when our galaxy was just beginning to take shape. And although the object's flyby will mark the end of our direct observations, the knowledge it has provided will continue to influence the field of astronomy for years to come. Moreover, 3I Atlas's passage through our solar system has served as a wake-up call for future interstellar objects. As astronomers continue to track objects like 3I Atlas, there's now a greater sense of urgency to prioritize their study. The upcoming flyby of other interstellar objects, like Oumuamua, offers a similar opportunity for groundbreaking discoveries. If we continue to improve our observational techniques and develop more advanced telescopes, who knows what else we might uncover about the ancient history of our galaxy and beyond. So, what does this all mean for our understanding of the universe? The data gathered from 3I Atlas is more than just a fascinating glimpse into the past. It has the potential to rewrite much of what we thought we knew about the formation of our galaxy, the solar system, and the conditions that existed in the early universe. The chemical composition of 3I Atlas tells a story that no other object has been able to reveal. It's a story about the very origins of the Milky Way, preserved in the form of water, carbon, and other molecules that have traveled across the cosmos for billions of years. The revelation that 3I Atlas formed in a metal-poor environment at temperatures below 30 Kelvin challenges our traditional understanding of galactic evolution. It tells us that the early Milky Way was a much colder, harsher place than we previously thought. And it shows us that objects from that era, like 3I Atlas, carry with them a chemical signature that can offer us direct insights into the conditions that existed before our solar system came into being. Perhaps most importantly, the discovery of 3I Atlas has highlighted just how much we still have to learn. This interstellar object has raised more questions than it has answered, and it serves as a reminder that we are just scratching the surface of what's out there in the vastness of space. The fact that we can study these ancient objects, that they can pass through our solar system and offer us their secrets, is an incredible opportunity. As we look toward the future, one thing is clear. The study of interstellar objects will continue to play a crucial role in our understanding of the universe. With advancements in technology and better observational tools, we will be able to track and study more objects like 3I Atlas, uncovering more mysteries of the cosmos. In conclusion, 3I Atlas isn't just a comet or a passing object. It's a time capsule from the early universe, a piece of history that has traveled across the galaxy to share its secrets with us. And as its journey continues, we must make the most of the time we have left to study it. The window to unlock its full potential is closing, but the knowledge we've gained will last a lifetime. Don't miss out on future discoveries like this. Subscribe to stay updated on the latest space exploration news, and leave a comment below with your thoughts on 3I Atlas. What do you think its deuterium-enriched water could tell us about the early universe? Share this with someone who loves space and deepens our understanding of the cosmos, because this is far more than just another interesting object in the sky. It's a glimpse into the very fabric of time itself.